Hello and welcome back. In this lesson, we are going to build on the concepts that we have learned previously about neural networks, which is feed forward layer, and the previous lesson in which we looked at basic concepts of how to think about vectors, how to think about dot product of vectors. And all of that is going to help understand what we discussed today in this lesson, which is about perceptron. So let me write that as select the ink. Perceptron learning, uh, perceptron learning, and in this, what we are going to essentially talk about is how we approach the W that helps us find the appropriate decision boundary. So let's say, for example, if we have data points, some are here, then we have some data points here, then we need to find a W which essentially helps us find that decision boundary, which is the boundary that successfully separates the two classes, right? And here I drew the decision boundary perpendicular to the vector W, and that is sort of the main point we will also look at. So to get started, what we'll do is first look at some of the changes in notation, and to do that I'm going to first draw the uh, architecture for the perceptron network. We have seen that previously, but this is just going to be an addition of what we already know. So let's clear that, and we have, let's say, some input, and this input is going to be R. So let's say we have R input, so we just type R, and from this input, um, R number of inputs, and what we mean by R here is number of features. So if you imagine a table with data, you have several columns, each column describing a feature and each row a sample. So that's what we are talking about. These are the features, and uh, for these features, then what we do is we are going to denote the input, which is P. We're going to denote the input P as a vector, which is R by 1. So one column and as many rows as the number of features. This input then goes into another box, which you probably already guessed, that is the for W, and then we also create another box down below here, which is for the bias. And together, apart from that, we also draw a circle here. That circle just represents that this is going to be summed here, and after that again we have another triangle which denotes the transfer function that we would be using to get the activation or output of the neuron. So let's draw a couple of more arrows in this to make sure everything connects. So we have one arrow that comes from there to here, and then we have another arrow that comes like that, then we have another arrow that goes from here, and then finally one arrow that comes out like that. So uh, here we can now start labeling these. This is our W matrix, the weight matrix, the one that we are uh, going to find out, and this entire discussion is on finding the appropriate values for this W. The shape is S by R. As you may have guessed, we have R number of inputs, and S is the number of neurons that we would have in this particular layer. Let's say the input is 1 for bias, which is lowercase b, and each neuron would have one bias, and so we have S number of uh, sort of biases. So the shape is S by 1. We put we do sort of the multiplication. So what this does is we simply take the w's, dot that with p's, add them up, and this gives us the value for n. That's what this is doing. And so we can type, say that this is the net input n, which has the shape again s by 1, because we get one. The reason why we are saying this is net input is because we're sort of combining all of this weight and then the raw input, then using that as input to this transfer function, and in here we are going to use the transfer function, which is the hard limb. So that gets us the output A, which is of the same shape, which is s by 1. So all in all, in here what we have is this is the input, then this part right here all the way to here, that is the hard limit layer, and that's what we would have right here as well, and this is our input. So the activation value, or A, that we calculate using the transfer function is going to look like this. A is equal to hard limb, and here we would calculate inside of this the values that we pass into the hard limb would be the value for n, which we are directly writing out here, which is w dot p plus b, and this is the perceptron network we have. So this is the perceptron network. So that is what we are going to imagine when we talk about updating w's and all the calculations we have. Of course, to keep things simple, we will not have very large number of neurons. So I think we just have one or two neurons, and similarly one or two output inputs p to the neuron. Now let's look at some of the symbols that we are going to use. It's going to be the same as what we had before, but with slight differences. For example, the W matrix that we have, W is equal to, we know that this is going to be of shape S by R. So what it means is in each row, in each of these rows, so let me draw that right here. So in each of these rows, it is going to represent values for one neuron, right, or the first neuron, then value for the second neuron, and so on. And this is going to be values for sth neuron. That's what we have. And if we now look vertically down, that is going to represent something else. So if we look down like this, so first column is going to represent the input 1. So this is going to be simply input number 1 that goes to each of these neurons, and likewise the last one is going to be the input R that is connected to all of these uh, neurons that we have. So to write this out, here is how we can do that. So the first thing we'll do is use subscript to specify which neuron we are talking about and which input we are referring to. The first row, when we say W, we are going to say this is for neuron 1. So these are all going to be 1 comma. So this is going to be common in this row. We have, then the second value would be 1 comma again, and third value would be same, and then finally we would have 1 comma again. And so the first value is going to be 1 comma 1. This is going to be input 1 going to neuron 1. Then we have the second input 2 going to neuron 1, and likewise input 3 going to neuron 1, and finally input R that goes to neuron 1. Likewise, in the second row, we are going to talk about neuron 2. So this is going to be 2 comma, and then for each of these W's we would again have input connected. So this is going to be input 1 that goes to neuron 2. This is input 2 that goes to neuron 2. Then this is going to be the input R that goes to neuron 2. So weights for all of those connections. And finally, if we go to the very last row in this W, this is going to be represented by S comma, and that is because this is going to be the Sth neuron that is there, and again this neuron would be connected to all the R inputs that we have seen in above rows. So this is going to be the first input connected to the Sth neuron, this is the second input connected to the Sth neuron, and this is the Rth input connected to the Sth neuron. And that is the entire view of the weight matrix that we have. To make things simple, in order to for us to write it out, what we are going to do is sort of put this in some sort of notation. What I mean by that is this first part that we have, which is right here, this row, this entire row, we are going to flip that over. So this is horizontal, we are going to flip it over to a column, and we are going to say that the Wi, which is the ith row in this particular weight matrix, is equal to, and then here we are going to put all of these values. So we are not saying 1 or 2. So if I say 1, then what we are essentially saying, we take the first row in that matrix, which is W1 comma 1, then we have the second value W1 comma 2, and then we have the last value as say W1 comma R. So all of the values in the first row, we say that we are now going to put that in a column represented by 1 and then the W. To make this generalized, so we talk about any column, we replace the number W with I, and we say ith W is equal to, and here we replace all the ones with i's, and so what we end up saying is this is the Wi comma 1. So input 1 to ith neuron, this is the input 2 to ith neuron, and then finally we have the rth input that we need to account for, and so we say the input rth input to the ith neuron in that weight matrix. So that is what we have, and let me clear this and write it clearly. So that's our W is equal to, and thus when we represent each row in this weight matrix W by this symbol IW, what we can then do is write our W matrix in a compact form, which would look like this. So we can write so let me just write it down here. We can write our W, which is going to be equal to, and like so, this is 1 W, and you'll probably say, hey Nilesh, this is a row, here we had flipped, how do we account for that? So what we can do is put a T there for transpose. Likewise for the second neuron, we have the W, and again we put the transpose for T, and finally for the Sth neuron, we say S, then we have the W, and we use the T for transpose. So that notation we would be using in this video to represent the W as we go through the iterations of updating it. And finally, the A, which is the network output for a particular neuron, can be written as A of I is equal to hard limb N of I, and here we know what N of I is. So hard limb this is going to be ith w transpose dot p plus b sub I, and this is uh, what this will get us is the output for a particular neuron in the network. And just to recall, the hard limb function, hard limb n, what this gives us is a value of 1 if n is greater than or equal to 0. If n is less than 0, then we get a value of 0. So that is sort of the basics of the notations that we have. Now with those notations, let's now get started and look at the very first case, which is the single neuron perceptron. And for this, you probably already know how the architecture would look like, or the figure would look like, but I'll still go ahead and draw it. Let's say we have these two inputs, P1, P2, and these come down here into this box, which is sigma, and each carries a weight. So this would have the weight input 1 going to neuron 1, and this is going to be input 2 going to neuron 1. And then we also have a bias term coming in from here, and then the output of this is going to be n. That's the net input to the transfer function, which we can show here. And remember, we are using the hard limb function, so anything below 0 on the x-axis is 0, and anything above that is simply 1. And then the output of this is a. So just to label this again, this is the input we have, and like so here, and then here what we have is two input neuron. So we just have single neuron, but then that neuron that we have has two inputs, and a in this case is going to be hard limb w p plus b. So that's all we have. Now to general, the equations that we would think about for this particular network is a is equal to hard limb n. Now we can be very specific what n is. So hard limb n, we know that that is w dot p plus b. So what is w in this case? The w in this case are these two values. So we can think of w as this this what you call vector. Let's say w 1 comma 1, w 1 comma 2, and then we have our p, which is p1, p2, and then we have the b, which is just the one neuron, so just one bias. And when we do the dot product, we get w11 dot p1 plus w12 dot p2 plus b, and we need to enclose this inside of the hard limb. So I'm going to move this equal to sign bit to the left. So this is going to be hard limb. Again, this is going to be inside of hard limb. So this is where we are. That's the equation we have, and we could have written this in a different form. We could have said, based on the notation we had earlier, hard limb, and this is just the first row we are talking about, and transpose p plus b, and that's one and the same thing. So with that, then what we already know is when we talk about decision boundary, what we are saying is that this equation that we just have inside of the hard limb, inside of the transfer function, this one, that is equal to 0. So we can say that n is equal to, this is 1 w transpose p plus b, which is equal to what we wrote earlier, w11 dot p1 plus w12 dot p2 plus b is equal to 0, and that is our boundary condition. And with this boundary condition, uh, uh, we can say that we can separate the classes, positive and negative class. To make this to convert this into example, you can assign some values to w1. Let's say that w11 is equal to 1 and w12 is equal to 1 as well, and the value for the b bias is -1. And if this is the case, then uh, what we can do is substitute these values in above equation, and what we get is, if we substitute it here, then what we get is 1 times p1 plus 1 times p2 minus plus -1 is equal to 0, and therefore we get p1 plus p2 minus 1 is equal to 0. And now what we can say is, if p1 is equal to 0, then p2 is equal to um, plus 1, right? How plus 1? Because let's say this is going to be 0 plus p2 minus 1 is equal to 0, so this is going to be simply, we bring this to other side, that becomes plus 1, we get p2 is equal to 1. So this could be one of our points, which is 0 and 1, uh, that we can look at. And then if p2 equal to 0, then what we get is our value for p1. So this is going to be p1 plus 0, and then -1 is equal to 0. So that gets a value for p1, which is going to be simply equal to 1. And so the data point we can think about in this case is 1 0. Now with just this information, what we can do is we can try and see if we can plot our decision boundary geometrically. So I'm here in Desmos, and what we can do is plot our points. So the first point that we have is p1, that is equal to, we said that it is equal to 0 1, and so that's the point we have. The second point, we said p2, that is equal to 1 0. That's the second point. And then what we have is our vector, weight vector, and weight vector, we said that it has value 1 1, so the weight vector is 1 1, and we can plot that. We can say w is equal to vector, and this starts at origin. Let's say this starts at origin, and then we go to 1 1, and that's our w. Awesome. So with this, we can clearly see that if we are trying to separate uh, the classes, then the decision boundary in this case is going to be uh, with 1 1. Right now it is going to be perpendicular to that vector, and so we can try and do that. So we can say p1 plus p2 is equal to, so -1 is equal to 0. So this won't compute in Desmos, so what we need to do is replace that p1 by x, p2 by y, and so now we see that we get that particular line, which is the decision boundary, and as you can see, it is perpendicular to the weight vector shown here by the red arrow. And graphically, then what we are saying is that let's zoom in a little bit, like so. And if I try and take a screenshot of this, and let's bring that in here and see uh, if we can write on it. So what we are saying here is that in this particular plot, the area on the right hand side of this, which is going to be this area, all of this, that is the positive class, right? And then all the area on this side is the negative class, and this line is the represented by the equation that we just wrote for n, which is w transpose p plus b is equal to 0. And if you remember, we said that if we put these values, uh, if we put the value of 0, p1 is equal to 0, then this left then we get a value of p2 as 1. And so if we just evaluate the left hand side, it would be 0 plus 1 minus 1 is equal to 0. And so as expected, these points p1 and p2 do lie on the decision boundary as one would expect. Now what we can do is take another point, let's say a new point which we have like a test point, and see if our decision boundary holds. So our decision boundary right now is given by this p1 plus p2 minus 1 is equal to 0. So that is what that line represents here. And if we then that's what that line represents. So we don't need that to evaluate a right now. So what we can say, a is equal to hard limb 1 w transpose p dot p plus b is equal to hard limb 1 1, that's the value for weight vector, and then the data point we are going to check, the test data point we have is 0 2, where p1 is 2 and p2 is 0. We already have bias as -1, so this gets us the value of this is 1 times 2 plus 1 times 0 minus 1, and so we get hard limb, and we get a value of 2 minus 1, which is 1. And so because this value is greater than 0, therefore our a is simply going to be equal to 1. And now we ask a question if this makes sense. And to understand that, what we can do is try and plot our point 2 0 on this particular plot. So x-axis 2 is right here, and y-axis 1 is right here. So this is the point we are talking about. This is the point 2 0, and it definitely is in the positive class, which is represented by 1, and that is what we have for a. So that did work perfectly. So the take home message in this discussion was that if we have value of w, if we have value of b, we can geometrically plot the decision boundary ourselves, um, and then we can try and test uh, if points are classified correctly in the respective class, positive class and negative class. But in reality, this is not that simple. So we have to uh, iterate over several values of w to arrive at the final w that gets us a decision boundary that correctly classifies the data points. What we could do is we could try out another point. Maybe let's try a new test data point that is, let's say, somewhere here, maybe this one. And for this point, the x-axis is -2, y-axis is 1. So the data point we are saying we want to work with right now, p is equal to -2 1. And so for this, again, we do the same thing. We say A is equal to hard limb, and this time I'm going to directly write the weight vector and write the vector for the input. So this is -2 1, and then we have the bias of -1. Again we pass this to the hard limb transfer function, and what we have inside of that is -2 plus 1. This is -2 plus 1 -1, and so this cancels out. What we are left is -2. So as you know, if the value inside of n is -2 or less than 0, then the hard limb says that, hey, that value for a now is 0. So that's why we get this as 0, and this is the value of 0, and we can clearly see that does make sense, because here the point -2 1 is on the opposite side of the decision boundary, which is in the negative class, and so you are correctly able to classify that point with a value of a is equal to 0. So that's so all this area is a is equal to 0 on this side, and all area on this side would be a is equal to 1. So on the line and to the right of it would be a is equal to 1, and this then is the decision boundary of two input neurons. So this what we have here is the decision boundary. So that's the decision boundary of a two input neuron, and we are saying that's a two input neuron because we have p1 p2, those are the values we are using, and that is exactly what we started out saying, that this is just one neuron but it has two inputs.